Welcome back. Today we're going to be understanding Avalanche consensus. Now there are three different types of consensus that I want to go through in this video, starting with traditional consensus, then Nakamoto consensus, and finally Avalanche consensus. By the end of this video, I hope you understand better how the Avalanche network works and just how big of a deal Avalanche consensus is in the world of computing. To understand Avalanche consensus, we have to start by understanding traditional consensus and how it works. Back in the 1980s, computer scientists wondered about how a network could come to a decision based off of a number of validating nodes within the network. So if a bunch of computers all run operations and they all come to an answer, they can agree on what the best answer is, known as consensus. And in a traditional consensus network, there's a central authority who decides what nodes are allowed to be in and out of the network. Now this works really well for something like a bank or a store, something where the transactions all happen under one umbrella and the central authority decides what nodes are allowed to make decisions. And so in a bank, if I want to wire money from one bank to another bank, the node in the first bank that's holding my money decides that they have that money and that it's mine, and then they send it over. And the node on the other side gets that transaction, puts it in their system, and then that is validated, and it's a safe and efficient way to move money. The only problem with this system is that a central authority has to verify membership for the nodes, and it has to decide whether this node is honest or unhonest, and every transaction has to go to every node in the network. Like I said, this works really well for centralized applications, but not so well for decentralized applications. So next we can get into Nakamoto consensus and how he fixed that problem. So Nakamoto saw the problem that they needed a centralized authority in order to make transactions, and he decided that there was a better way to do it, and that was through decentralization. How do we make a network that a peer-to-peer can transfer money without having to worry about the security of that money? And he created what was called Nakamoto consensus. And Nakamoto's consensus revolutionized the way that money can be transferred on the internet through Bitcoin. And he, of course, named the consensus after himself, which is pretty funny. And the idea is that if I want to send a Bitcoin or an asset or anything to somebody, I put up my private key, and then I create part of what is a new block. And so there's no nodes involved yet. This is just me sending something to someone else. But in order for that new block to be publicly displayed, a group of miners or validating nodes have to do a cryptographic or a math function related to that private key in order to create that new block and validate that that's a true transaction. And so miners are rewarded, and that's why it's called proof of work, by doing the work in the math to make this new block. This would make a lot more sense if I had asymmetric key cryptography video, but if you go online and look that up, essentially that's a breakdown of what happens between the sender and the receiver, but the miners are the nodes that make sure that's all true. And so then the public key of the receiver is put out, and that also is mathematically, I guess not really mathematically related, but the transaction data is mathematically related to the private key of the sender and the public key of the receiver. And that's what the miners are looking for in their math to verify that this new block is true and that the data is true. Now this is all fantastic when Bitcoin is small. There's not a lot of transactions running through it, but once we get the network running with a lot of people trying to move stuff, these cryptographic math equations get really hard. And so the miners have a really hard time to keep up with this, and they use a ton of power. And that's the main downfalls of Nakamoto consensus, is the amount of CPU required to actually run the network. So the solution to that, Avalanche consensus. So the last type of consensus we looked at used proof of work, Bitcoin, the original of the original. But as other blockchains have realized that proof of work is not that fast, they've moved on to a proof of stake model. Now, proof of stake is commonly misused or misunderstood as being the way that a network actually decides the transactions or verifies the transactions. That's not true. These are just symbols of, or basically the foundation of how it's set up in order for the nodes to validate the transactions. So Avalanche uses a proof of stake model where people in the network holding AVAX token stake their token into a pool and they become part of the proof of stake network. And based off the amount of stake they have relative to the rest of the network, this decides how likely they are to be picked for query. And the query is Essentially, do you believe that this transaction is valid or invalid? And a really common analogy for this is if you're in a room of people and you ask them, do they like pizza or chicken wings? And every time, no matter how big the network becomes, they ask the same number of people if they like pizza or chicken wings to start. So we're going to set our K value to 3, and we're going to ask 3 nodes that have been randomly selected in the network to decide if they like chicken or pizza, right? And so each node will make their own selection, and we're going to pick this top left node, and he's going to pick pizza as his original decision, right? And then he's going to do K equals 3 people he's going to ask of his friends, do they like chicken or pizza? So he's going to randomly select 3 more and ask them if they like chicken or pizza. And 2 of his friends decided they like chicken, and the third one decided they like pizza. And in this case, the majority is chicken. So he's going to change his answer to chicken. And in under less than 1 second, all of the nodes in this network will query with each other until eventually a decision is decided, which makes this lightning fast. Every transaction can be finalized in less than 1 second, which makes it one of the fastest blockchains out there and rivals even transaction companies like Visa. And at this point, you might be asking, what happens if one of his friends decides he doesn't want to answer? Then we have to wait, right? Wrong. There's a timeout on each one of these nodes, and if this guy takes too long, he'll randomly select another node to take his place in order to keep the network from stalling or slowing down. And this is what makes Avalanche so fast. The reason it's called an avalanche is because once the decisions have been made, there's an avalanche of decisions that creates the final consensus of the network. But like I said, the speed of Avalanche is due to the ability for this, like I said, the ability of all the nodes to concede or make a consensus very quickly, but it's also so great because it doesn't require all of the math that Bitcoin does, all of the math that proof of work models do, where computers have to spend all this time and waste all this energy solving frivolous math equations. Proof of stake on an Avalanche or Snowball protocol can very quickly complete transactions and very quickly make decisions. And that's what's so great about Avalanche. So I hope this helped you to understand the Avalanche network a little better, and I'd like to continue this series with breaking down the DAG model that Avalanche is on and breaking down some of the GameFi options that it's going to be having in the future along with its subnets. So thank you, and I hope you enjoyed.